Hi there, Augie Kennedy here with the final test for Super Awesome Calculus. I'm a little bit sunburned today. I was at the Giants versus the Marlins to watch the Giants. I got to see Lincecum, Kane, and Vogelsong. It was pretty awesome. But anyway, back to math. We have the test today. Now this is the last test for Super Awesome Calculus, which means that it's basically the last thing that we're going to do together. So, let's just get to it. There was no big problem last time. I just figured I'd test you on each component right now. So, without further ado, here comes the test. Hi there. Alright, I hope the test went well for you. Let's go ahead and let's solve the question. So the first thing I asked you was a very basic question that could have phrased it however you wanted. What is the volume of a cylindrical shell? Well, this one, it was a multi-part question. Well, what is the volume for a cylindrical shell? This one's pretty easy. It's 2 pi r h. Because, here's your cylinder. There you go. Alright, now if you want to talk about the cylindrical shell, it's going to be 2 pi x f of x. It's pretty simple. Makes sense. You got your f of x. You got your x. I mean, it makes sense. F of x is y. X is there. Makes sense. So, how would you use that to find the volume of a solid? Well, a solid of revolution. Well, it's pretty simple. If you've got a function that looks like this, you can take a cylinder, an arbitrary amount of x distance, and you can put a shell there at the height of the function. And basically you can take the integral of all of those shells, the infinitely many shells throughout the function, and you'll get an idea for the volume. And of course you'll want to use that instead of slicing when, for instance, in this case, I don't know this function, but I would assume that this would be an easier dx integral to solve than to take dy's with slices. In general, I can't say this with absolute certainty, but I'm pretty sure it is. If it would be a dy integral with slicing, it'll be a dx integral with cylindrical shells. If it's going to be a dx integral with slicing, it's going to be a dy integral with cylindrical shells. So in this case, I'd rather take a dx integral, so I'll use cylindrical shells. So that's basically around the type of answer that I would have liked. I mean, if you were close to that, that's good too. Alright, the next question. I asked you to find the area of the region bounded by the following curves. Y equals x squared, and y equals 4x minus x squared. This might look familiar to you, because this was basically an example that we did, except instead of 4x, it was 2x minus x squared. So this is pretty easy. The first thing you're going to want to do is you're going to find out which one's on the top and which one's on the bottom. Well, if you graph, first you might want to find points of intersection. And you set the two equal to each other, remember? So x squared equals 4x minus x squared. And we get 4x, or 2x squared minus 4x equals 0. which will yield x equals 0 and 2. So those are going to be our points of intersection, 0 and 2. I don't really know what they're going to look like, but it's basically going to look like this. So we want to find the area in there. It's going to look something kind of like that. Excuse me. So, what that means is that this 4x minus x squared is on top, and x squared is on the bottom throughout the whole interval. So it's going to be a very simple integral to set up, because it's just going to be the area is going to equal that minus that between 0 and 2. So the area of the region bounded by those curves is the integral between 0 and 2 of 4x minus x squared minus the second function that was on the bottom, which was just x squared. Rid of these little squares up there, dx, which is the same as 0 to 2, 4x minus 2x squared dx, which is great, which is 2x squared minus 2/3 x cubed, yeah, between 0 and 2. Obviously at 0 it won't equal anything because it'll just be 0. And at 2 you'll get 8 minus 16/3, yielding a final answer of 8/3. And that's the area, 8/3. All right. Now the next question was an application of finding volumes of solids of revolution. I asked you to find the volume of this object, of the solid obtained by rotating the region bounded by the given curves about the specified axis. And the curves I gave you were very simple. Y equals 2x, y equals x squared about the x-axis. Once again, you can find the points of intersection. 2x equals x squared. You're once again going to get 0 and 2. And if you want to go ahead and find the actual points, it's going to be 0, 0, and 2, 4. Right? Yep. 2, 4. Just plug in the 2, plug in the 0 to the original function, you'll get your y value. All right. Now, let's go ahead and plot it out. Let's graph it. All right, we got 2x. It's going to be a line. Oh, shit. Sorry. It's going to be a line like that. X squared is going to be a parabola like that. So we've got, if this is going to be 2, and that's going to be 0, what we're going to want to do is we're going to want to rotate this region right here around the x-axis. So let's go ahead and do that. And we get kind of like one of those Pac-Man type lip things. And the right thing to do here, as you can see, this is a great candidate for slicing. We've got line, line, and then a little lip inside. So if we take a slice, we can very simply see that we're going to get a washer, or torus, or whatever you want to call it, a donut, whatever. Now, remember, when we're identifying the radius of the washer, we have to realize the outer function and the inner function. In this case, the outer function is the top one, which is, in this case, 2x. And the inner function, therefore, is x squared. So, what that means is that if area equals pi r squared, because it's the area of a circle, it's going to be the area of the outer minus the area of the inner. And it turns out that that is area equals 4x squared minus x to the 4th. And it's easy to see why, because pi r squared, there you go, 2x squared minus x squared. Alright, so now we have our area. Now what's the significance of that? Well, we know that volume is really just the integral between the boundaries of the area. So volume equals, we have the boundaries of 0 and 2, a of x dx. But we know that this is the same as the integral of 0 to 2 of pi r squared, which is 4x squared minus x to the fourth dx. We go ahead and we can combine a couple steps here. Take the pi outside the integral and go ahead and use the fundamental theorem of calculus. So we get 4x cubed over 3 minus x to the fifth over 5 between 0 and 2. And we know that 4x cubed, if you plug a 0 in, and x to the fifth, if we plug a 0 in, will be 0. So we only have to worry about the top boundary, 2. And it turns out that that's going to give us pi times 32 thirds minus 32 fifths, or 64 pi 15ths. And that is the volume. Not too bad, is it? Not bad at all. Now, the next question I gave you was kind of a challenge, kind of just something to think a little bit differently. I gave you a solid, and I asked you to tell me something about what the solid is. So the solid I gave you was the integral between 0 and pi of pi times 2 minus sine x squared dx. So that is the volume of the solid. So what I want you to do is tell me about the solid. So you're going to look at what's in there. Well, the first thing you could say is that it's a solid of revolution, because that's basically what we've been covering. Well, what are the bounds? Well, obviously the bounds are 0 and pi. So we can say that we rotated an area between 0 and pi. And what did we do? What did we rotate? Well, we rotated this function. 0 less than y, 2 minus sine x. How do we know that that's what we rotated? Well, and we rotated it, we flipped it around the x-axis. How do we know? Well, because we can see the formula pi r squared in here. We can see it. Pi times 2 minus sine x quantity squared. That's just the same thing. So that's something that you could say about that solid, if you were so inclined to do so. Now the final question I gave you was basically just a super big recap on the average value of a function. I asked you to do 3 things with this function. The function I gave you is f of x equals x minus 3 squared on the interval 2 to 5. Okay? And what I asked from you, I wanted you to find the average value of f on that interval. I wanted you to find a c, a number, so that the f of the average was that number. And I wanted you to sketch the graph of f and a rectangle whose area is the same as the average. So, let's try it. First, we find the average value. This is really easy. Part A. Average value is 1 over 3, 5 minus 2, times the integral between 2 and 5 of x minus 3 squared dx. I'll even make this easier. 5 minus 2. So you can see the mechanics. Now, the second step, 1/3, we're going to use the fundamental theorem of calculus here. So it's going to be x minus 3 quantity cubed over 3 between 2 and 5. You're going to go ahead and we're going to plug those numbers in. You'll find that you're going to get 1/3 times 5x minus 3 is 2, cubed is 8, 8/3 minus 2 minus 3 is -1, -1 cubed is -1/3. So we're going to add, change the minus to a plus, plus 1/3. We're going to get 1/3 times 9/3, which is 1/3 times 3, which is 1. So the average value of this function, f_av, is 1. f_av equals 1. Okay, that's the first thing we know. Second, we need to find some c's. Some c's in here. All right, that are representative of the integral at its average. So through the fundamental theorem, or through the mean value theorem for integrals, we know, remember, that fc equals f of the average. All right, well, what does that really mean for us? Well, it means that that would mean that c minus 3 squared is going to equal the average, 1. So we square it, and we get c minus 3 equals plus or minus 1. C equals 2, -2, and 4. Now it's going to equal, it's going to equal 2 or 4. So C equals 2 or 4. Okay? So f of c, 2, and 4. And finally, we graph the function. This is very easy. It's just a parabola, right-shifted 3. And f of average is 1. So we got 1. And how far does the rectangle go? Well, it goes from 2, 5. So there you go. That rectangle has the same area as the average value of that function. So, that is all she wrote. Which means that you get a smiley face. Great job, everybody. Thanks so much for watching. I've really had a great time. If you don't watch, that's okay, because then you're not seeing this. But anyway, I've got one more thing that I'm going to say, and I'm going to make a separate video about the final exam if you'd like to take it. And I kind of secretly hope that I can come back for Calc 2. Alright, bye-bye everyone.